on the lecture. All right, so it looks like I got the recording started, so let's go ahead and get started. So today we're going to be pushing forward into some new topics. This is going to be moving from chapter 14, which was psychometrics and mixtures, into chapter 15, which is basically our chemical reacting mixtures, and we're going to focus on combustion. Now with combustion, we can, in thermodynamics, consider it a pretty hot topic, kind of a bad pun. But we can start it off, our combustion lectures with a joke, because all combustion jokes are guaranteed to have a reaction. And so with those bad puns to start us off, let's go ahead and get started on kind of the material here. So the objective of this is to cover combustion, so we have a good idea of what's going on in terms of our chemical reacting systems. And the reason that we want to do this is combustion is one of the most common sources of heat for all of thermodynamics. So when we talk about heat coming from combustion, we can say propulsion systems, so jet engines, Brayton cycle, that's going to be using jet fuel. So you're going to have jet fuel in your engine. That's going to give us our propulsion system. It's going to give us our power for our plane. In terms of like natural gas power plants, you're going to again have fuel coming in, combustion providing that power for your Brayton cycle. Transportation, you have your auto, you have your diesel cycle for your cars and your trucks. We have fuel that's going to be combusted in those engines. That's where our heat source. And if you think of just general heat, well, heating, one of the most efficient ways to do that is still with a fuel. Yes, we have renewable ways of doing that don't necessarily need a fuel source, but heating up fuel or heating up water, we could do that with like a natural gas heating. So again, combustion is a really powerful source of heat, and it's very important in modern thermodynamics and just modern life in general. So that's why we want to spend all of this time, because it is a wonderful source of heat. And in thermodynamics, the big goal is to take heat and convert it into work. So that is why we will spend time talking about combustion. Now, previously, we've only really considered combustion as kind of a simple heat addition. So if we talk about simple heat addition, this was basically Q in or Q dot in. We just said for like the Otto cycle, the diesel cycle in this class, we said, let's simplify it down with that air standard assumption. We didn't have to worry about what was going on inside the system. We just said heat got added. And so we want to dig a little bit deeper now. We want to say, okay, what's going on in terms of actually getting that heat in? We're going to have a chemical reaction. We need to figure out how much fuel now we would need to put into our Otto cycle to get that amount of heat, temperature rise that we had in our engine. And so that's kind of where we're going to head towards this in this term. This week we're going to kind of introduce it. Next week we're really going to get into the detailed thermodynamic side of the problem. And so again, main goal is to figure out, okay, how are we going to now use a fuel to provide that heat? Because we're going to pay for fuel. We don't necessarily pay for the heat. We pay for the fuel that we're going to combust and turn into heat. And so that's why we have to kind of be able to take it one step further, look at the chemistry of combustion. And so combustion in and of itself is going to be a chemistry problem. So it's going to be taking two substances, putting them together. We're going to get a chemical reaction that's going to release energy. That's where we're going to get the heat. And so simply put, the combustion process is going to be our reactant. So we're going to have a fuel. We're going to have a oxidizer. We're going to put those together, provide a little bit of heat, combust the fuel, turn that into our products. But in doing so, we're going to release a whole lot of energy. And so in terms of the process, this is the chemical reaction. This is what we wanted to get. This is the Q dot out. And so this is the heat coming out of that reaction. This is what we're most concerned with. And so this is what we're going to be looking for by the end of next, or into next week. We'll be able to actually start trying to determine what is the heat transfer and heat transfer rate for our chemical reactions. Now, I will note that because this is chemistry, this is going to be a molar problem. So chemistry deals with moles. We're going to have to go back to the molar basis. So again, molar analysis in applied thermo is very, very important. And so before we get started, I wanted to just point out some fuels. So not all fuels are going to be the same. The amount of energy that we get from each fuel is going to depend on the chemical structure. And so I thought I'd start us off by just taking a look at some different fuels. We have some gasoline, which has a pretty good energy content per volume. Diesel is a little bit better than gasoline. But again, we can get some very dense fuels with high energy content per volume. We have some that are low because these are generally more gaseous. And so it doesn't necessarily mean that these fuels don't have a whole lot of energy. It just means that we'll have to have a larger container to essentially store them to get all of that heat released. But I do like to mention that we have quite a few different fuels that we'll now be able to look at, and we can look at how much energy can we actually release from each of these fuels. And so that is the whole purpose of this chapter. The purpose of the discussion is to now be able to pick out a fuel, figure out how much energy we're going to need, how much air we're going to need, and then try and use that to kind of figure out what's going on inside of our engine to provide the heat that we would need to run our power cycle. Now, I do want to point out that most of this chapter is going to be denoted to hydrocarbons. Now, hydrocarbons, we'll see this quite a few times, take the form of C to the N and then H to the M, where these two are variable. And so we can take a look at the back of the textbook. We'll see some different fuels, but most of the fuels we'll take a look at are hydrocarbons. This is one of the major sources of fuels that we have. They're quite powerful, have a lot of energy inside of them. So these are the most common, but there's also other forms. So we could have, say, like ethanol. So these generally have the form of C to the N, H to the M, and then we'll have the OH kind of denotion at the end. So slightly different chemical structure. And then we could have something like methane, so methane CH4. And so there's different fuels that we can take a look at, but generally all of these are going to follow kind of a similar structure, just about how many different elements are going to be in the molecule itself. Okay, so that is just a little bit of an overview of where we wanted to go. So let's go ahead and dive into the combustion problem and start with the basics. So today we're going to focus on what's going on because we have to do a little bit of chemistry. And so I know it's been a while for some people for chemistry, so we're going to take it slow and build our way up into the full process. Now, whenever we're dealing with combustion, we are going to be dealing with the chemical reaction. So the chemical reaction that we're looking at is going to be inside of a reaction chamber. We need to bring in things to react to be able to get our product. Now, simply put, for the chemical reaction, we are going to bring in our fuel. Now, I said fuel traditionally will be the hydrocarbon. And so we'll just pretend right now we're going to just use a hydrocarbon. Could be anything, but we bring our fuel in, and then that fuel has to have something to react with. And so whenever we think of a fuel, we also have to provide an oxidizer. And so the oxidizer provides the oxygen that is required for the combustion process. Now, in terms of oxidizers, what we want is oxygen, which would be O2 in its stable form. So we have O2 providing the oxygen, so we need fuel plus O2. However, when we think about where could we get oxygen that's readily available, and the easiest thing that we said as well, there's oxygen in the atmosphere, there's oxygen in air. And so if we want to essentially provide this oxidizer, we are going to grab the most convenient thing. And so if we're driving our car, well, just driving around, we don't carry a tank of oxygen with us. We just pull oxygen from the atmosphere or the air itself. But the downside of this is air is going to be a mixture. So we've talked about air being a mixture of several ideal gases. And so while we do get the oxygen that we would require for our combustion process to happen, we also have some additional byproducts that are going to happen in our reaction because we have a mixture And so we don't just have oxygen. We have oxygen, we have nitrogen, we have some other gases. And so if we want to take a look at this on the molar basis, well, the air itself is composed of many different substances. We said we had nitrogen, and so on the molar basis, nitrogen accounts for 78.1% of the air. And then the next thing we'll have is the oxygen. So the oxygen is what we wanted for the oxidizer. This is going to be about 20% of, or 20.9%, I should say, of the molar basis of air. So these two are our biggest components, but oxygen is the second component, and second by some distance. The third component that we could consider is there's a little bit of argon, and so this would be 0.9% on a molar basis. And then there's other trace gases. And we'll note that these are the other trace gases, and these account for the very last 0.1% of the atmosphere. And so air has quite a few different gases, and we'll note that the trace gases that we generally consider, there's a little bit of helium, there's a little bit of hydrogen, there could be some carbon dioxide, and of course we could have some water vapor with some humidity. And so that can be considered in these trace gases. Now, if we're going to bring this in for our reactant, we're just using air, that means we're going to have to consider nitrogen, we're going to have to consider argon, and we can consider everything else. And so that gets to be a little bit complicated in terms of our setup, because now air is going to be, we're looking at an element by element, and we have to consider the full structure of air. And so that would be a little bit complicated. But what we want to do is we want to develop a simpler model for air that we can use as we progress forward through the rest of this class. And so that's what we're going to do on the next slide. Now, before we move to the next slide, I want to take a look at this reaction chamber to kind of go over what we're doing. So now we have our fuel, we have the air coming in. And so what we're going to do is we're going to provide a little bit of a spark into the system. This is going to cause the fuel to reach the ignition temperature so we can begin breaking down the molecule. When that combines with the air, that gives us our reaction chamber. And then once the chemical reaction is complete, we have the products leaving the system. And so this is the general setup that we're going to do. And so, again, what we're looking to do in this first part is just simplify our model of air so we can develop it a little bit quicker. We don't have to slog through quite as much math, quite as much accounting for the later problems. And so to do that, we said, let's make air into a very simple model. You'll note that, again, this is for just air. And we said, well, if we looked at the air structure that we had before, there was a number of components, but really there are two main components. Or should we say elements? I'll call it components. So if we go back one slide here, we said two main elements. We had nitrogen and oxygen. Those accounted for almost all of what the gases in the air were. So if we go ahead and come back here, we said, all right, two components. We are going to use nitrogen. And so in the air itself, we said, well, that was going to be about 78.1% in the actual case. The second gas that we had was oxygen, and we said oxygen accounted for 20.9% of the gas on a molar basis. And we said, well, let's take a look at this. 20.9, he said, if we round that just a little bit, let's make this be oxygen has 21% of the total molar volume. And so that works out. And so then we have the 78.1. And we said, well, in terms of combustion, nitrogen is going to be what we refer to as an inert gas. We don't care about it because what we wanted is we wanted the fuel and then we wanted the oxidizer. And so what we really cared about is the oxygen. We rounded that to the closest value. We said, well, nitrogen will be inert. It's not going to do much for a reaction. Same things with these other trace gases. We said those aren't going to really hopefully do much in terms of reacting. And so let's just go ahead and bulk in these, the argon and the nitrogen, just bulk it all together. And what we'll get is, if we do that, we'll just assume that this goes to 79%. And so it's a reasonable kind of rounding. And so we said we can now just assume air is composed of two gases, oxygen and nitrogen, because those are two biggest values. And so now for our oxidizer, this is going to be oxygen plus nitrogen, and then we'll have our fuel. Okay, so simplified it down, but we're going to want to go one step further, and we're going to see why this comes into play a little bit later. And so what we want to do is we want to set up our air model in terms of this oxidizer. So again, everything is focused on oxygen in terms of combustion, because that's what we care about for the chemical reaction. So we want to do this so when we get to the chemistry portion, we can do all of the balances per oxidizer. So basically, if you want to think of it, in psychometrics, we did everything per unit mass of dry air. We're going to try and set up air as per oxygen or per oxidizer content. And so what we're going to do is we want to use 1 kmol of air or oxidizer. And so if we have 1 kmol of oxidizer, we have to add in some amount of nitrogen to this reaction. So again, what we're going to want to do is we want to figure out how much fuel we have, how much oxidizer we need, and then figure out how much air we're going to actually have to provide. And so to actually find this value, we said, well, if we're going to set this value to 1, this value was 21%. And so we could just go ahead and set this up as a ratio. So I'm going to go ahead and remove this, and we're going to say it's going to be 0.79 divided by 0.21. And so this is going to represent the number of kmols that we have of the nitrogen. And so doing this, we get the model that we're going to use, and this is going to be 1 kmol of oxygen plus, now we're going to have 3.76 kmol of nitrogen, and we're going to use this as our basic air model. So this is what we'll refer to as air moving forward for all of the chemical reactions we need to do. Now, I know this may seem a little bit strange, but I'm going to point out in this model, we are going to keep nitrogen in the system. However, it is going to be an inert gas. And so what we mean by the inert gas is that when we put it into the system, what we really cared about, again, is the oxygen. We don't really care about the nitrogen, but we do need to keep it in the reaction system, because if we go again back to this setup, we see that it's about 80% on a molar basis. So most of air is nitrogen, and so when we essentially use air for the combustion process, nitrogen is going to need to be considered, because that's going to represent kind of a large mass moving through the system, and we're going to have to heat that up in the combustion process. We have to keep track of it because it's going to come out as our product. And so if we go over here on the product side, this nitrogen just kind of goes through, but the energy that's released, it's going to take some of that energy. And so we do need to keep the nitrogen involved in the reaction. We can't just get rid of it, because it's going to play an important part in determining the temperature of the fluid or the combustion products after the reaction. And so that's why we're going to keep nitrogen, even though it's inert. And so that what we mean by inert is it's not going to interact with the fuel to form any product. And so it'll be important. We'll talk about this. We'll see this in some of the coming lectures, but I want to introduce it now, just to kind of explain why we can't get rid of nitrogen just yet. Now, at this point, since we're talking products, we can figure out what are going to be the main things that are going to come out of this combustion reaction. Now that we have our fuel is going to be a CN H to the M. And so if we figure out we're going to have carbon, we're going to have hydrogen, we're going to have oxygen, and we're going to have nitrogen. And the main substances that we're going to form at the exit, we'll have the nitrogen coming through as an inert gas. We'll have some carbon dioxide, which will form. We'll also form some water vapor. And so those are going to be the main things that we'll see in the products. We can also have some extra air. So if we had a little bit more air, we can have some excess oxygen at the exit. So those are the main products that we're going to consider in our actual system. Now in real combustion, we could have some additional byproducts. And so some of the notable ones would be just some base carbon. We could have some base hydrogen. We could have some carbon monoxide. We could have some remnants of our fuel. And so when these particular parts are visible or seen in our chemical products, we can usually make a note that our combustion process would not be complete if we see some carbon monoxide, some parts of our fuel still left over. And so generally we want to try and have perfect or complete combustion. We'll talk about what that is coming up. But these are going to be things that we would note would occur in real combustion processes if we didn't quite get that perfect chemistry to occur. And so basically what would have happen is if we didn't provide enough air, our fuel wouldn't fully convert into carbon dioxide and water. And so we'd have carbon monoxide, we have some hydrogen, carbon, and just remnants of the fuels. So those are the main things that happen, particularly if it's not perfect. Perfect. And yeah, so that's sometimes when the cars can backfire and you can have some flames coming out. You can also have some byproducts, particularly like older cars that maybe didn't quite have the fuel mixture right, particularly if it's running really rich. You can have your car having basically fuel coming out of the exhaust. And so you're paying for the fuel, but you're not being able to actually use that to run your engine. And so when we do our analysis, we're going to be assuming a perfect system, a perfect reaction. So we're going to focus on these variables up on top. Now, before we move on, there's one more very important reaction that I want to point out. And so if we go to high temperatures and high pressures, which most engines now actually operate at, we can actually bring nitrogen from being that inert gas into play at very high temperatures, and that forms NOx, which is generally considered a basically environmental pollutant. And so we're going to just neglect this. We're going to try and keep this combustion model simple, but I do want to point out that at very high temperatures, nitrogen stops becoming an inert bystander for combustion and kind of starts to get into the chemical reaction and form the NOx that we would see. But we're going to neglect this for our class, but I do want to point it out because I do think it's important to know what actually happens and what kind of simplifications we're making so we can get a good understanding of what's going on versus trying to go too far kind of into the topic at this point. Okay, so that is how we're going to set up air. Particularly, we should note that this is the model that we're going to need, and we're going to develop that a little bit further here in the next few slides. Okay, so let's go ahead and move on to the next slide here. And we're going to talk about mass conservation. So this is where things get a little bit more detailed. We are going to spend a little bit of time talking through this because it's very important to kind of understand what's going on. So in terms of our conserved quantities, we will always note that up until now in Thermo 1, Thermo 2, fluids even, we always said mass is conserved. And so we had mass conservation. Now, what we're going to do, we're going to take a step further. So I think in the last topic we had was psychometrics. When we started breaking it down, we did conservation of mass for water, conservation of mass for our dry air. And so we're going to do conservation of mass now. We're going to do it for each element. And we are also going to do it at the global scale. So mass is still going to be conserved in a chemical reaction system. However, to figure out what's going on inside of the system, we do have to do a molar analysis to figure out how the system is reacting, because this is chemistry. So to figure out how we're changing molecules, how the elements change, we do a molar analysis for each element. And this lets us know how the reaction is proceeding. So if we wanted to note, this could be oxygen, this could be hydrogen, carbon. So we don't worry about if it's in a molecule. We just look at what the individual structure, what the individual element as the base is for this analysis. Now, in terms of the conservation equations, what I want to make sure to note is mass will always be conserved. Moles are not conserved. So we do have to be very careful about our analysis, what form we are going to be using, how it's going to come together. This is going to be very important to keep track of, because now we're doing chemistry and thermodynamics all in one problem. And so let's just go ahead and kind of look and see what's happening, what we mean by each of these statements, because by themselves they can be a little bit confusing. And so what we're going to do is we're going to do some chemistry. And so in chemistry, we had a way of doing reactions, and that was looking at our stoichiometric balance. And so we're going to start with the chemistry side of things. And so in terms of kind of a simple system that we can do an analysis on is, let's say on the reactant side, we bring in some hydrogen. We bring in some oxygen, both in the stable forms. And what we want to get in terms of our product is we want to get some water to form. So oxygen plus hydrogen gives us water. And so in terms of chemistry, we wanted to set up a stoichiometric system. And so we would say we would have the hydrogen coming in. We would add that to some oxygen. This then goes through the reaction chamber to give us our products. And the product was H2O. So we had water being formed. Now, I know it's been a while for chemistry, so this is why we are taking it a little bit slow going back through this. But what we then said is, well, we needed to do a balance, so we added some stoichiometric coefficients. So we'll call these A, B, and C in front of each of these substances. And then what we wanted to do was an element by element molar balance. So this is what we mean by a molar analysis for each element. And so in terms of the system, it's fairly simple. We only have two elements that we're dealing with. So we have first our hydrogen. And so for our hydrogen, we would have to first balance this. And so we want to figure out how many hydrogen molecules do we have on each side of the reaction. So in terms of bringing in, we only have hydrogen occurring on the first term here. And so we'll note that the elements that we bring in would be the stable form, so it would be bonded with itself. And so we have H2. And so when we do it per element, we're looking at the single element of hydrogen, not the stable form with the bonded to itself. And so we'd say, well, there are 2 hydrogens per 1 kmol of this stable system. And so we would have to look at this again per element. And so we bring the 2, we bring it out front. And so the balance begins by saying we have 2A, so 2 times the stoichiometric coefficient for our hydrogen molecule. And so this then has to equal the same number of hydrogen molecules that we'd have on the right-hand side of the equation. We notice on the right-hand side of the equation, we just have the 1. We have H2 times C, and so we bring the 2 up. And now we have 2C, and we'll note that the stoichiometric coefficient for A has to equal the stoichiometric coefficient for C. And so that was pretty straightforward. And so we can go ahead and do this again for oxygen. And so in terms of oxygen, we have the same setup on the left-hand side. We have 2 molecules of oxygen in this system. So we have 2 times B. This now has to equal the number of molecules that we have of oxygen on the right-hand side. So we have 0. We have 0. We have an oxygen here, but we note that there's no subscript here, so we just have the 1 molecule. So we bring the 1 out front times C. So this would be 1 times C. And so we're able to say, well, C now is equal to 2B, or if we wanted, we could say B is equal to C over 2. And so, again, this is the basic chemistry, chemical approach that we can use for our system. Okay. And so if this is what we want to do, let's go ahead and take this a little bit further. And let's just say we wanted to solve for 1 kmol of oxygen. And so we wanted to let C equal 1. And so again, this gives us 1 kmol of oxygen, or not oxygen, 1 kmol of water being formed. And so we need to figure out how much of each individual substance do we need to put in to get 1 kmol to form. And so if we put in C is equal to 1, we'll note that the A coefficient also has to equal 1 kmol. And so we just have 1 kmol of oxygen being formed, or coming in, or hydrogen coming in, because that is on the H. And then we can say we have the second term here. Second term is B, that would be C over 2. And so we would have 1/2 kmol coming in on the oxygen side. And so if we were to write this out, we'd have 1 kmol of hydrogen plus 1/2 kmol of oxygen. This goes to 1 kmol of H2O, or water. Now, what I want to point out here is on the molar analysis that we've just done, we had 1 mole here, we had 1/2 mole here, so we had about 1.5 kmols of substance that we brought in on the reactant side. Now on the product side, we only have 1 kmol of substance on the right-hand side, and so what we'll note is 1.5 does not equal 1, so we can't say the moles balance. So this is what we mean by moles are not conserved, because if we do the balance like we've done here, we've tracked all of the individual molecules, but the total number of moles of the substances don't necessarily line up. They have to, again, on the per molecule basis, but again, the total combined moles coming in, going out, will not be the same. So that's what this first statement was saying. You cannot just use this balance, add up the moles, get the total number of moles of your system. And so that was just a proof of that calculation. So generally we will, but for the most part, we'll be dealing with gases. So basically we'll assume everything is in the vapor state generally. We'll be able to get to that point, but for most considerations, everything will be in vapor. We'll talk about some maybe of the exceptions, but generally for a lot of our analysis, we'll be able to assume most things are going to be vapor. But that's a good question. We'll talk about cases in the next few lectures as we get a little bit further into the chemistry portion. Okay, so now that we've proven that the mole values are not conserved, let's go ahead and just prove that mass is conserved. And so if we take a look at the conversion, so just noting that to get the mass of a substance, we need the number of moles times its molecular weight. And so we'll need to look up some molecular weights to do this. And so let's just do that calculation. So molecular weight of hydrogen This is going to be 2 kilogram per K mole. I'm going to do a little bit of rounding here. I'm going to try and keep it simple, just kind of to show what the effects are. I'm not going to go into the fine resolution here. So then we'd have the molecular weight of oxygen. So oxygen was about 16. We had 2 molecules, so this would be about 32 kilogram per K mole. So again, just a little bit of rounding here. And then if we realized that we needed the molecular weight of the H2O, so our water, well, we'd have 2 hydrogen, so that'd be 2 kilograms plus 1 oxygen. 1 oxygen we said was 16, so this gives us about 18 kilogram per K mole, accounting for a little bit of rounding that I've done. Okay. So now that we've done the lookup for the molecular weights, we can go ahead and push forward. And we said, okay, we wanted the mass of the hydrogen. So mass of the hydrogen would equal the number of moles of the hydrogen times the molecular weight of hydrogen. And so what we're going to do is we're going to come over here to our stoichiometric balance. We said, well, the coefficient that we had for this is going to be what the number of moles are. So in this case, we're looking at hydrogen. Hydrogen's coefficient was A. So I'm going to note that we'll use the stoichiometric coefficient now to determine the number of moles. And so in this case, we had a stoichiometric coefficient A equaling 1. So 1 times 2 is going to equal 2 kilograms. So bring about 2 kilogram of hydrogen in. Then we can repeat this for the oxygen. So the mass of the oxygen that we would have, well, we have molecular weight of oxygen 32. We need then the number of moles of the oxygen. And so we go over here to oxygen. Oxygen's value for N, this would be B for our stoichiometric coefficient. B was 1/2. So we have 1/2 times 32. It's going to equal 16 kilograms. And so before we go too much further, we said, all right, let's add up the mass. These two are our 2 reactants. So we had 2 kilograms coming in over here. We had 16 kilograms coming in over here. These two combine. This gives us 18 kilograms coming in on the reactant side. And so we have, again, 18 kilograms coming in. And so let's go ahead and check that now with the final state. So we want the mass of water that we've now created. So this would be the number of moles of H2O times the molecular weight of H2O. And so when we do this calculation, we have the number of moles. So this would be C according to our setup. So number of moles would be C. C was equal to 1 in our case because we set that up. So 1 times the molecular weight. Molecular weight is 18. And so we have 18 kilograms of water. And so over here we now see, yes, we had to use chemistry, but mass was conserved through the process. The number of moles was not, but the total mass was conserved, and element by element, the number of element or molecules of each element remain the same. So we're going to be doing some chemistry. So this is just kind of a quick reminder of how we were going to do it. And so let's go ahead and see what happens when we introduce some real combustion reactions in our system. So that's what we're going to do here on the next slide. So we are going to do a stoichiometric combustion for a hydrocarbon. Okay. And so if we remember, we're going to be doing the combustion for fuel, and then we had air coming in. Now for the hydrocarbon, this was, in terms of the setup, this was C to the N we used before. Really, the PowerPoint is not liking me. I'm going to change it a little bit. We're going to say this is going to be C to the Y, H to the Z, just to kind of keep track of things. So yeah, this is just our hydrocarbon coming in. And so we are going to set up the stoichiometric reaction. Now, in terms of setting this up, like in the previous example, we got to set something equal to whatever we chose. And so when we do the stoichiometric reaction for any sort of fuel or combustion process, we generally want to set it up as a per fuel analysis. And so the reason we'll do this will become clear once we get into the energy components of modeling the stoichiometric reactions. But basically, if we think of like back to kind of psychometrics, it was really convenient when we found everything on the per unit mass of dry air. And so what we want to do is figure out what is everything kind of on the per mole basis of the fuel that we're adding in, because then we could just figure out how much energy is released per mole of fuel. We can then scale up everything that we would need for that setup. So what we're going to do is we're going to solve this for 1 kmol of fuel. And so this is just the setup that we are going to use for our system. And so again, the known setup that we're going to have is that we have fuel plus the air. This is going to go to the products. And so we'll also note that these products will also release some energy. Hopefully for combustion, we're giving the energy off, not having to consume it. And so what we want to do is set up the full stoichiometric balance for this system. And so in terms of this balance, we know that it's going to take some fuel in. And so we'll do it for the hydrocarbon. This is going to be C to the Y, H to the Z. And so we're going to leave this in a pretty broad form because we can change the molecular structure for most hydrocarbons. We can scale up the complexity of the molecule. We could scale down. This is just the general form. So again, this should give us a pretty good idea of how to solve any sort of problem. And so what we wanted to do is we said this is going to be per 1 kmol of fuel. And so what we're going to do is we're just going to put a 1 for the coefficient out in front of our fuel. And so everything has to get scaled by this 1. Okay, so at this point we said then we have to add in the air because that's the other part that we have for our combustion reaction. And we said, okay, what was the model we had for air? And so if we go back a few slides, we said, well, what we had is 1 kmol of O2 plus the 3.76 kmol of nitrogen. And we said this represented the model that we had for air. And so we'll note that that is air. And then we said, well, we need to put a stoichiometric coefficient out front. So let's go ahead and do that. We'll have A be the representative coefficient for air. Okay, so those are the two reactants coming into our system. And so now we have to get the products. And so in terms of the products that we've had, we said we had first, we're going to get some water vapor. So we had some H2O. And so that was our first one. The second one that we're going to expect if we have a perfect combustion process would be carbon dioxide. And then the last thing that we're going to have to note is that we will have some nitrogen. And so in terms of putting some stoichiometric coefficients in, we'll have a B, we'll have a C, and we'll have a D coefficient. And so we need to set up and do a balance for all of these elements now. So let's go ahead and do this balance. And so we want to work through this element by element. And so the first thing that I always like to do is just go ahead and start with carbon. And so starting with carbon, we have some carbon in our fuel on the left-hand side. We'll note that this is the only carbon that we'll be bringing in. Our air doesn't have any carbon in it. We're assuming, again, no carbon dioxide in the air. And so what we have is we have the Y, we have the 1, And so on the left-hand side, we just have the y because it's y times 1. And then what we can do is we can say, well, that has to equal the right-hand side of the equation. And on the right-hand side of the equation, the only place that we have carbon dioxide is in, or carbon is in carbon dioxide, which has 1 carbon molecule times C. So we'll note that Y has to equal C. And so what's really kind of cool to note is the amount of carbon dioxide molecules that we're going to generate is purely dependent on the number of carbon molecules that we have in our fuel. So we have a high carbon fuel, a large amount of CO2 will be generated. So kind of a cool observation. So after we have the carbon, we can move on to the second one, which is the hydrogen. In terms of hydrogen, we have 1 hydrogen here times Z. So we'll just have Z number of hydrogens based on our fuel. And then if we go over to the product side, we only have hydrogen in the water. We have 2 hydrogens in the water. So we have 2 times the stoichiometric coefficient, which is B. And so if we go ahead and resolve for B, B is going to equal Z divided by 2. Okay. And so moving forward, we can repeat this for oxygen. So in terms of oxygen, we have, well, over here we did it on 1 kmol of oxygen. We see we set this up so we had it really nicely done for our oxidizer case, and then made our stoichiometric balance a little easier. So we have the 2 inside of here. We take this 2, we multiply by the 1 kmol in here, and then that kmol gets multiplied by A. And so we have 2 times A, number of oxygen on the left-hand side. And then we need the number of oxygen on the right-hand side. And this is where it gets a little complicated because we have an oxygen in the water. So we'll have 1 oxygen there, so plus B. And then we also have 2 oxygen in the carbon dioxide, so plus 2C. And so we can rearrange this. We can find A. This is going to equal B divided by 2 plus C. But we'll note is B is dependent solely on the fuel, and C is also dependent solely on the type of fuel that we have. And so we'll note that A, this is going to equal, we substitute in Z divided by 4 plus Y. And so the number of molecules that we just solved for air to get this balance to work out is dependent solely on the chemical structure of the gas or the fuel. So how many hydrogen molecules, we divide by 4. How many carbon molecules, we just add that in. And so we have a very nice relationship for the amount of air that we have to bring in, and we note that just on the chemical structure of the fuel. And so that's kind of a nice result. So that's the big takeaway so far. So we can now figure out how much air we need to bring in. Now let's go ahead and just finish up our balances. And so the last one we have is nitrogen. And so if we do this for nitrogen, well, we have this 3.76 times the 2 times A. And so we have 3.76 times 2 times A on the left-hand side. And we'll note that we have 2 times the stoichiometric coefficient of D on the other side, dividing through by 2. What we note is it will always end up being, for this case, 3.76 times the stoichiometric coefficient A. And so this can get substituted in because nitrogen didn't have a reaction. It was just a bystander going through the process. And so there we go. We've done our basic stoichiometric setup for combustion and for our hydrocarbon. And so at this point, that's where we want to kind of start kind of wrapping down today. But before we do, I want to point out the last little bit here, and that is in this form, A is equal to Z over 4 plus Y. This gives us the minimum amount of air that we would need. If we had any less air than this value, so if A ended up being less than what this calculated number is, we would not have enough air for complete combustion. And so this is the, I want to say, pure stoichiometric balance. And so this is, it's good. We'll have perfect combustion in terms of our analysis. But again, it's really close to basically setting ourselves up to waste some fuel. And so what we're going to see in the next slides is we'll talk about how can we slightly change this, how can we use some metrics to now look at how can we make sure that we get complete combustion, can we add a little bit of extra air in to make ourselves give ourselves a little bit of a buffer room so that we don't waste any of our fuel by just having it go through and not go through the chemical reaction. And so that's where we're going to pick up in tomorrow's lecture. We're going to talk about the common metrics. We're going to talk about adding excess air, talk about measuring excess air, and then we'll be able to work an example doing all of those details. So again, that is the end of today's lecture. This is just the introduction to our combustion processes. If you have any questions, please let me know. Otherwise, I will see you tomorrow in lecture. All right, have a good evening.